Imagine you're trying to find the lowest point in a valley, or perhaps the optimal setting for a machine. In many real-world problems, we want to find the input that minimizes some output, like finding the best parameters for a model to minimize its errors. This is fundamentally an optimization problem, and gradient descent is a powerful technique to solve it. In machine learning, this valley often represents a cost function or loss function. This function measures how bad our model's current predictions are. Our goal is to find the model parameters that result in the absolute lowest cost, meaning our model is performing optimally. This landscape can be complex, with many dimensions, but the principle remains the same: find the bottom. Gradient descent is an algorithm that helps us find this minimum iteratively. Starting from an arbitrary point on our cost landscape, we repeatedly take steps in the direction that leads us steepest downhill. Think of it like a blindfolded person trying to find the bottom of a hill. They feel around to find the steepest downward slope and take a small step in that direction, repeating until they can't go any lower. At the heart of gradient descent is the cost function, often denoted J of theta. Here, theta represents our model's parameters, the weights and biases we want to optimize. The cost function takes these parameters as input and outputs a single number, quantifying how much error our model makes. A lower just theta means a better model. To know which way is downhill, we use calculus, specifically the derivative. For a single parameter, the derivative tells us the slope of the cost function at our current point. If the slope is positive, we need to decrease our parameter. If negative, we increase it. For multiple parameters, we use the gradient, which is a vector containing all these partial derivatives. It literally points in the direction of the steepest descent, so we move in the opposite direction. But how big should each step be? This is controlled by a crucial hyperparameter called the learning rate, denoted by alpha. A small learning rate means tiny steps, leading to slow but stable convergence. A large learning rate means big steps, which can lead to faster progress but also risks overshooting the minimum, oscillating, or even diverging entirely. Choosing the right learning rate is critical for effective gradient descent. Putting it all together, the gradient descent algorithm is an iterative process defined by this update rule. New theta equals old theta minus the learning rate multiplied by the gradient of the cost function with respect to old theta. We repeatedly update our model parameters in the direction opposite to the gradient, scaled by our learning rate until we converge to the minimum. This continuous adjustment is how our model learns and improves. In summary, gradient descent is a powerful optimization algorithm used to find the minimum of a function. It works by iteratively adjusting model parameters. We use a cost function to quantify error, the gradient to find the steepest path downhill, and a learning rates to control the size of our steps. By continually moving towards the minimum, gradient descent enables machine learning models to effectively learn from data,